Today we are going to study about gravitational fields. It's actually very important part for day-to-day life. We know without gravitational field we can stay on the Earth's surface, no water, no atmosphere. Then gravitational force should be there to form magnetic field also, because magnetic field is created by the convection currents of the magma. Then without magnetic field no water, right? We can study that later. Then anyway, gravitational field is a very important part. Then first you should know what is the meaning of a gravitational field. Gravitational field means this: a space, any space which can form forces on masses. Any space which can form forces on masses is defined as a gravitational field. Then first we are going to study gravitational law. Gravitational law means attraction between two point masses. We are going to consider here very small masses compared to distance between center of gravities. Consider any two objects, the space, right, point masses. They are under attraction. Always gravitational forces are attractive forces. One of them action, another one reaction. Both are same. Then assume two masses, one of them capital M, another one simple m. Separation between them r, that means distance from center to center r. They are under attraction, that is the gravitational force. After studying this equation, we can find mass of the earth, we can find mass of the sun, we can study motion of satellites and everything. Therefore very important equation we are going to study. Actually, this force is proportionate to product of the masses, not each mass. Action reaction means forces are same. If force proportional to one of them, one side force will be greater. Therefore, force proportionate to product of them, mm. And this field obey inverse square principle. What is that? Force is inversely proportional to square of the distance between the particles. The next one, F proportionate 1 over R squared. Then you know, F should proportionate to product of these two terms, mm over R squared. Proportional constant is known as universal gravitational constant. It's a fixed value, right? It's a fixed value. F equals G capital M simple M over R squared. It's standard equation. You have to learn this and you have to remember this equation. What is G? G is equal to 6.674 10 to the power minus 11 units. You can derive Newton square meters per kg minus 2. This is the gravitational constant. Then a force, G gravitational constant, universal gravitational constant, capital M mass, simple M mass, both should be point masses, are distance between center of gravities of the masses. This is the first formula we have to learn. Now we can study about motion of earth around the sun. We can find mass of the earth, we can find mass of the sun, and we can study about satellites. I'm going to discuss first how to find mass of the earth. Consider this is the mass, right? Radius of the earth we are given 6.4 10 to the power 6 meters. We know gravitational field intensity, that means gravitational acceleration on the earth's surface, G. I can mark small mass here, then you know force mg. They are under attraction. Both forces should be equal, mg and mg. Top one is the force exerted by the earth on the object. Another mg is force exerted by the object on the earth. Then we can apply that previous equation. F equals G capital M simple M over R squared. You can find mass of the earth because you know F is mg, this attraction. It is equal to G capital M simple M over R squared. Simple M is getting cancelled. Then you have G capital M is equal to GR squared. Actually, this is also very important. When you're doing questions, if you need G capital M, instead of G capital M, you can use G and R. What is G? Acceleration on the corresponding planet. Acceleration closer to the corresponding planet. R radius of the corresponding planet. Then if you need G capital M product, instead of that you can use GR squared. Right? Now here you can calculate mass of the earth. You know, GR squared over capital G. Then G, you know, normally 9.8. Later we can calculate that also. 9.8, radius of the earth 6.4, 10 to the power 6. That square you have to take. Don't forget that. Divided by G. 6.674, 10 to the power minus 11. You can simplify this, right? It's homework. Its value, I'll give you 6.14, 10 to the power 24 kilograms. This is the mass of the earth, right? Very, very simple. Next one, I'm going to explain how does satellite orbit around the earth. Satellite means this: if any object orbits another one, that object is a satellite. Electron is a satellite which moves around the nucleus. Earth is a satellite which rotates around the sun. Moon is a satellite which rotates around the earth. Then any object orbits another one, it's a satellite. Then we are going to study motion of satellites first, right? Consider this mass, capital M, and consider another mass, simple m, which is moving with the velocity of v or u, right, m. You know, if momentum is there, it should try to travel along a straight line, but it is under this attraction. Due to this attraction, it should bend. It should bend. It tries to go horizontally, but due to the attraction, gravitational attraction, you know, G capital M simple M or R squared. Due to the attraction, its path will be curved. Assume it comes to here. Again, it tries to go this way. You should know this velocity can't change by this F. Magnitude constant, only direction can change because force is acting perpendicular to the velocity. You know, to change the velocity, force should act in the same direction. But here, force is acting perpendicular to that. Therefore, speed should remain unchanged. It tries to go away from the earth again. Again, you can see it experiences gravitational force. Therefore, it should travel. It keeps on traveling along a circular path. Always, it has to bend towards the center of the planet or whatever the object. Okay, then it tries to go this way. Due to the gravitational attraction, it bends. Then you can see it travels along this kind of circular path. And this is circular path I told you. If this separation is r, we need circular motion principles also. You know, in circular motion, we know force equals m tangential velocity squared over radius, centripetal force. And we have another equation, you know, m r omega squared, b tangential velocity, r radius of the circular path, m corresponding mass. In the second equation, you can see m mass, r radius, omega, angular velocity. You know, angular velocity is equal to 2 phi over time period. We need this equation also. And you should know this also. If this force is more than, right, if this force is relatively large, what will happen? Compared to this mv squared over r, then it travels along this kind of path and falls onto the Earth's surface, whatever the planet, if f is greater. If f is less, if is not sufficient to keep this object along this circular path, then you'll see its radius increasing gradually increasing, and it goes away from the attraction. Therefore, there's some kind of equilibrium. When it travels this way, force is acting, it bends, again it tries to go this way, force is acting, it bends. Some kind of equilibrium is there. Then, centripetal force means here gravitational force. Then we can find relationship among them. I'm going to draw a new diagram. Right? Mass is here, simple m. Its velocity as mu. Attraction this way f. Here also attraction is there. This one capital M. Assume radius of the circular path is capital R or simple R. Now I am going to apply both equations together. What is that? Gravitational force equation, G capital M simple M or R squared, and circular motion equation mv squared over R. Both we have to combine. F should be equal to G capital M simple M over separation squared R squared. I told you it is center to center distance should be equal to M. Here tangential velocity U squared over radius of the circular path. It travels along that corresponding circular path continuously. R. Now we have one relationship. Simple M is getting cancelled. 1R can be cut. Velocity we have square root Gm over R. We know Earth rotates around the Sun, approximately in a circular path. There's a special reason for that elliptical path. We can study that later. For the moment, assume Earth rotates around the Sun along a circular path. If you know distance between Earth and the Sun, it's 1.5 10 to the power 11 meters, then you can calculate mass of the Sun. It's a very nice thing, right? I'm going to calculate that first. Sun is here. Earth is rotating around this. Mass of the Earth simple M, mass of the Sun capital M. I told you distance between them 1.5 10 to the power 11. We need only this and gravitational constant, then you can find mass of the Sun. Then how do you apply that? Assume this Earth travels along a circular path, right? It's 99% correct. Then actual mass also you can calculate. Then I'm going to apply that equation we learned. F equals G capital M simple M over R squared. This is attraction. R means center to center distance. Attraction, this I told you it is in some kind of equilibrium. If this force is not there, Earth will travel in a tangential direction, right? Then to keep this Earth along this circular path, Sun has to attract. Then that attraction should be equal to our circular motion equation. What is that? M, I'm going to take here R omega squared, right? M R omega squared. Simple M, that is mass of the Earth, it's getting cancelled. G we know. Then you can calculate mass of the Sun. R cube omega squared over G. I told you R 1.5 10 to the power 11 squared omega we know 2 pi over time period, 2 pi squared 4 pi squared, and we need time period squared. 2 pi over t is omega. I'm going to write it here. What is the time period of the Earth around the Sun? We know it is 365 days. We have to convert into seconds. 365 days. It should be multiplied by 24 to convert into hours. After that 3600 to convert to seconds squared. Then R cube we need here 6.45 squared, and G also, we know G 6.674 into 10 to the power minus 11. Simplification is up to you. Okay, the answer I can give you 210 to the power 30 exactly. That is the mass of the sun. It's very nice. Right. Then next one I'm going to consider small another explanation. Then for any kind of satellite, we can do that also. Next one I'm going to find velocity of a satellite orbits the Earth in a near orbital. Near orbital means compared with radius of the Earth, it can be 50 kilometers, 100 kilometers, right, closer to the Earth's surface. We can find velocity of a satellite which is orbiting the Earth, right? Let's do that. Earth, radius 6.410 to the power 6 meters. Satellite is there, closer to the Earth, assume 50 kilometers above the surface, approximately closer to the radius of the Earth. Now it travels along this kind of circular path. We know that. We studied that. Then how define that velocity? Let u be the velocity, let m be the mass of the satellite. Distance we know, it is approximately equal to radius of the Earth. Again, same equation you can apply. What is that? F equals G capital M simple M over R, separation approximately 6.4 10 to the power 6. Then R squared, and I'm going to take, now I'm going to take mv squared over R because I want to find velocity. mv squared over R. You can see mass is getting cancelled. And I told you, we found that G capital M product, we can consider small mass which is placed on the Earth's surface. We know attraction m naught G, right? We can find that force. You know, m naught G is equal to attraction of them. G capital M simple m naught over distance between center of the Earth and center of the mass, R squared. M naught can be cut. Then I told you, instead of G capital M, you can write what? GR squared. Then here also, instead of G capital M, we can substitute GR squared over simple R squared equals MV squared over R. M was getting cancelled. Then you can remove M again. Then here, R squared can be cut. RG root is the velocity of the satellite orbiting the Earth in a closer orbit. You can calculate this. Radius 6.4, 10 to the power 6 we know. Radius of the Earth, G is 10, we can take approximately 10, square root of this. Then you can see 64, 10 to the power 6 root, actually 8,000 meters per second. It's huge velocity. 8,000 meters in 1 second. It travels 8 kilometers in 1 second. Actually, same manner you can calculate the velocity of the Earth. You'll see closer to 30 kilometers per second. Velocity of the Earth, we can calculate. V equals R omega, right? Radius, I told you, distance between center of the Sun and the Earth, 1.5 10 to the power 11. Omega, you know, 2.5 over. Time period of the Earth, 365 days, right? Then you can find velocity of the Earth. It will be 30 kilometers, closer to 30 kilometers in 1 second, right? Very huge value. This is a basic application of this Newton's gravitational law. Then we did the same kind of questions, now a little bit different one. Consider two point masses, one of them m, another one 5m. Assume separation between them 60a, whatever the value. They are released in space. How do you find point where they collide? You know, They're under attraction, equal and opposite forces. Always you can see when they are moving, always forces equal, opposite. Therefore, at any instance, you can see resultant force acting on the system 0. Therefore, actually, we have two methods. First method, center of gravity of them can't change. Fine, no resultant. No resultant acting on them. If there's no resultant acting on a system, right, center of gravity should be stationary or it should travel with uniform velocity according to Newton's first law. Then here, initially they are stationary, they're released. They should collide at the center of gravity. We know forces are equal. Therefore, center of gravity can't change. Very easy to find center of gravity. M phi m, mass ratio 1:5. Then separation should be in the opposite ratio, phi n by. Then this distance will be 5a. This distance will be simple a. This is the point where they collide. This is the first method. What is the first method? No resultant force acting on the system. Therefore, no need to change the center of gravity. No need to change the center of gravity. Then center of gravity is located m phi m. 1:5. You know that 5:1 ratio. At that point they should collide. Actually 50a here. This one 10a. 60a we have divided in the opposite ratio. 1:10, 1:5, 5:1. This is the first method. Second method, you can think. At the beginning, they are released from rest. If they are released from rest, momentum 0. Momentum 0. At the beginning, momentum 0. At any instance, they should keep that because no resultant. If there's no resultant, we know conservation of momentum should be conserved along that line. Therefore, at the beginning momentum 0, at any instance, they should have together 0 momentum. Then for example, assume this velocity here u at a general position, this velocity v, then you'll see one of them m into u. I'm going to apply this way. Then another one minus 5m into v. Then you can see 5mv equals mu. Then u equals 5v. What is the meaning of that? When a small one travels a certain distance in the same time, right, for a small time interval, big one should travel 1/5 of that because u is 5v. It travels 5 times always. Then again you can see they should collide at the center of gravity. Why? This travels 5 times always small one. We saw u equals 5v. Therefore, they should collide at the same point because they should travel always 5 times. They should travel always 1 time. Then that ratio 5:1 always. Then 2 methods we have. Right. If you are given a finite object, instead of point masses, you are given finite object. You want to find the point where they collide. For example, consider there's a mass radius 2a, another one a. Assume this mass 8m, right? This mass m, and assume separation of them 93a. Then when they collide, definitely distances traveled should be in the opposite ratio. Why? Always force resultant 0. Therefore, always momentum should be 0. Simple a, that means simple m, should have 8 times of velocity of capital M. We can apply conceptual linear moment. At the beginning 0. At any instance, you can take 8m into u. Another one you can take m into v. Then you will see v is equal to 8u. What is the meaning of that? That means if big one travels a certain distance, small one should travel 8 times. Therefore, they can travel always in the ratio 8:1. But you know, when they collide, there should be a separation 3a. Then freely they can travel only 90a because initially separation 93. When they collide, separation 3a, therefore they can travel only 90a freely. Then the distance you have to divide in the ratio of 1:8. Then this will travel 10a, this will travel 80a. This is also basic application, right? Then after that we can start next theory part. Uh, Actually we are doing satellites again. I gave you small questions to learn this equation. Then we are going to study next part, gravitational field intensity. For any field we need that. Gravitational field intensity. Intensity means any field, force acting on unit mass or force acting on unit charge. Then force acting on unit mass is defined as gravitational field intensity. How do you find that? Assume this mass capital M. You want to find at a distance of r gravitational field intensity. I told you that is force acting on unit mass. Generally we can mark mass m here. Then we know attraction. F is equal to G capital M simple M over r square. But what is gravitational field intensity? Force acting on a unit mass. Therefore both sides we have to divide by simple m to find force acting on unit mass. Then F over m, that is the field intensity, Gm over r square. Very easy to memorize. Then you have to remember this equation also. This is gravitational field intensity, and you know force over mass means that is the gravitational force acting on the object. Then it accelerates towards Earth. How much that acceleration? Force over mass. Resultant force F only acting on that mass. Then F over m, I told you field intensity, and is equal to positional gravitational acceleration. If you want to find acceleration at any point, you can use this. Or it is equal to force acting on unit mass. Both are same. This is positional gravitational acceleration or field intensity. Force acting on unit mass. Then it's better if you can remember this equation, right? Otherwise always you have to derive, right? G dash, G capital M over R square, outside of this object. What is G dash? Force acting on unit mass, and it is equal to gravitational acceleration by force over mass means acceleration. Only the force acting on this object there, F we know, G capital M over R squared, G capital M simple M over R squared, divided by simple M, that is force over mass, acceleration. Then corresponding acceleration or gravitational acceleration, or if you want to find force acting on unit mass, you can use this equation. Its units you can see newtons per kilogram because force acting on a unit mass. Then we can draw a graph to represent variation of field intensity around any object, any planet, right? If it is free, like this. This is the y-axis, you can see. This is the x-axis, you can see, right? Here, on the surface, we can mark some value here. It's we know G dash, equation G capital M over R squared. R is the distance. Then normally we can take right side as the positive direction. If you consider right side as positive direction, gravitational force towards the earth, therefore it's better we can draw that in negatively, because This side force towards this. If you take right direction as positive, then opposite force you'll draw as negative. It's better. Then you can see it's a deep curve. Why it's so? Here you can see in this equation G dash is inversely proportional to R squared. That means when R is doubled, gravitational field intensity is reduced by 4 times. If R is increased by 3 times, gravitational field intensity is reduced by 9 times. Then rapidly decreasing curve. Right? Here also we can draw on the left hand side. Then you can see if mass is placed here, attraction towards the center, it is acting in the right direction. Then we have to draw it as positive. Right? It's also with distance, negative x direction, rapidly decreasing and comes to 0. Why? G, that means positional acceleration or gravitational field intensity, is inversely proportional to square of the distance measured from the center. Right. Actually, we have to draw according to our syllabus outside of this. But actually inside of this very simple thing. Inside of this earth, it's earth or whatever the object, if it is uniform, straight line. We can prove that. Very simple, right? That kind of straight line. If you want to find that, I'll explain it here. If you want to find inside of this object gravitational acceleration, you need only this mass to find that. Right? Then here, if you want to find G, you need this mass because our equation G capital M over R square. Outside shell doesn't affect. Right? It was invented by Newton. It is not in the syllabus. It is known as Newton's shell formula. Right? No need that one. You should know inside of that it should be a straight line. We can find that. Assume total radius capital R, inner radius simple x, inner radius. Then you can calculate that. G dash inside. G over, now I'm going to find at a distance of x. Then R means x squared. How to find mass of inner part? Very simple. Total mass divided by total volume, that is density. Density into an inner volume, it's inner mass. It's all level. Total mass can be divided by total volume, 4 by 3, 5 capital R cube. It should be multiplied by volume of this inner sphere. 4 by 3, 5 x cube. Then you can see x squared is getting cancelled. 3 over 5, 4, 5 over 3 is getting cancelled. X squared is getting cancelled. Then inside we have, right, G capital M over R cube into X. It's like y equals mx. Right? In addition to our syllabus, this is actually very simple thing. That's why I explained that. Then inside of that, you can see this kind of straight line. Then anyway, you should know on the Earth's surface, on the surface of the planet, on the surface of the object, we can find maximum field intensity. This is the maximum value that can be created by this planet. Here maximum value. Inside of that decreasing. Outside also decreasing rapidly. Inside it's linear. Outside it's a rapid decreasing. Right. This is a basic variation of field intensity. Finally we know field intensity means force acting on a unit mass. Force acting on unit mass, it is equal to gravitational acceleration. And you can see here, we can find always 2 points which has the same acceleration. Inside of the earth 1 point, outside of the earth another point. Same gravitational acceleration G dash we can expect inside and outside both. But we are studying outside of this sphere always. This is gravitational field intensity. Actually, we can calculate gravitational field intensity on the Earth's surface. It's 9.86, and we can find gravitational acceleration on the sun's surface, right? We can find that it is radius of the sun 7 × 10⁸ meters. If you want to find acceleration on the sun's surface, g dash, that means positional gravitational acceleration or field intensity, you can use that equation. What is that? G capital M over R squared. G 6.674 10⁻11 mass of the sun. We just calculated it was 2 10⁻30 kilograms. Then you can find radius 7 10⁸ squared. Then you can find acceleration on the sun's surface. It will be 273.2, right? Simplification is up to you, right? 273.2 meters per huge value. Meters per square second, right? This is field intensity. And you should know gravitational potential. Next topic is gravitational potential. What is gravitational potential? We are doing so many questions with gravitational field intensity and Newton's basic equation. We are doing more questions, but for the moment we have to complete basic theory part also. Gravitational potential is the next topic, right? Gravitational potential. What is that? You know normally potential energy, mgh. You know that. Assume this mass capital M. At a distance of r from any planet, any object, right? Any mass, point mass. Here potential means, this is a definition. Before that definition, you should know this basic. You know, when mass is raised to a distance h, we are doing work done mgh. We have to mgh. Then other way around, if it is brought down, work done by us should be minus mgh. Think it. If object is moved away from the earth, small distance, little radius, you know, mgh. That is the work done by us. That energy is stored. But if you move that one towards the earth, work done by us will be negative, right? Towards the earth, work done by us negative. mgh means work done by us when it is moved away from the earth. When it is moved towards, work done by us negative. Then gravitational potential is defined like that. Definition for any field, potential means very simple thing, energy needed to unit mass from infinity to point considered. From infinity to point considered. If you want to move that to the infinity, you have to do work. It's not easy. But if it is brought towards, automatically it comes, work done by us negative. Therefore, gravitational potential is a negative value, because energy needed to bring unit mass in the electric field, it's a unit positive charge. Energy needed to bring unit mass from infinity to point considered is defined as potential at that point. Energy needed to bring this one. I drew a regular path because it's path independent. Gravitational field is a conservative field. Whatever the path, energy same, right? Then energy need to bring 1 kilogram from infinite to point considered is defined as potential. No need to know how to derive that equation. You should know only the equation. It's with minus sign. Minus G capital M over R. Units. Joules per kilogram. Because we brought only unit mass. Energy stored in unit mass. Work done, energy needed to bring unit mass from infinity to point considered is defined as corresponding potential. Why it is negative? If it is moved away, we have to do work on that, but we are not doing when it is brought from infinity to that point, right? Automatically it comes due to the gravitational field, then work done by us negative. Then you can't remove this minus sign. Don't do that. It's very important part. Always energy, gravitational energy is a negative value. I'll explain that later, right? Then here potential V equals minus Gm over R. What is capital M? Mass of this big one. R, distance from the center of that object to the outside. That is the potential. V equals minus Gm over R. It is negative. You can't remove that negative point. Negative sign you can't remove. Never. And this is the potential. What is potential energy? Potential energy means energy needed to bring any mass. For 1 kilogram, this much. Then how much for M? Very simple. That is W, work done, minus G, capital M, that mass M, work done by us negative, Gmm over R. You have to remember these equations. They are very important. This one joules. Potential joules per kilogram, energy stored in unit mass. Mg over R means energy stored in simple M. That's always negative. It's like we are indebted to Earth by energy. It's true. We are indebted to Earth by energy. If you want to make it positive, you have to go to infinity. Why? When you're going to infinity, R goes to infinity, then it will be 0. Then you know, maximum value that can be taken by a negative answer is the 0. Maximum value that can be taken by a negative value 0. Then you can take maximum value 0 at infinity. Otherwise, always energy is negative. We can't make it positive. We are indebted to Earth by energy. Then basically you have to memorize this equation. Minus G capital M over R potential minus G capital M simple M over R potential energy. Potential is an absolute value, right? Corresponding to that point, we can find potential minus G capital M over R, potential energy G capital M simple M over R. And this was very important. If two masses are there, assume one of them simple M, another one capital M. If you find energy of simple M, you may say minus G capital M simple M over R. But actually this is energy of both. This is not energy of one of them. This is energy of both. MGH also. Not energy of that mass. MGH means energy increase of Earth and that object both. But we know Earth can't move, therefore that object goes down again. But actually MGH means energy increase of Earth and object both. If you move some object upwards a distance h, you will say, I did only MGH on that object. But actually you increased energy of both Earth and the object. MGH means energy stored in both. Here also G capital M simple M over R means energy of both masses, right? Here also, in this part also you can see energy means energy of that big planet and the object both, not only one object, right? It was invented by Kepler, right? It's a very nice thing. Total energy G capital M simple M over R. Then we can plot potential variation around this planet, right? Then what is potential? Basically, once again, energy needed to bring unit mass from infinity to point considered, right? Then when it's moved away, we have to do work. That is positive. Towards that, negative. Right? Energy need to bring a point mass from infinite to point considered is defined as potential at that point. Then this is total energy. We can plot potential variation around this planet or object. X-axis, Y-axis. I'm going to draw potential here. And there's a nice relationship. I told you G is equal to minus G capital M over R squared. Not minus. G capital M over R squared. Potential, I told you, minus G capital M over R. You can see some relationship between them. G dash, positional gravitational acceleration or force acting on unit mass, newtons per kilogram. This is joules per kilogram. You can see nice relationship between them. What is that? If you divide this potential equation by radius, again, equals Gm over R squared. Then you can see it is equal to, what is that? It is positional gravitational acceleration or field intensity. This is positional gravitational acceleration or field intensity. Then we have another nice relationship. Potential gradient is the field intensity. Potential over R. Potential difference over distance difference, that is potential gradient. dV over dr, right? It's also very helpful when you are doing questions, when you are plotting graphs, right? Potential gradient is equal to minus field intensity or positional acceleration, or minus gradient is equal to positional gravitational acceleration. Then basically we studied many equations. First one, attraction between two masses, F equals G capital M simple M over R squared. Next one we did potential minus Gm over R. Next one we did potential energy minus G capital M simple M over R. Now here we know there's a relationship. What is that? Potential gradient is the field intensity, right? Now we can plot potential variation. We know potential is always negative value. I told you we can't make it positive, right? We can't make it positive. Then closer to the earth I can mark, closer to the earth, whatever the planet, I can mark minus value, that is minus Gm over R. After that you can see V proportionate to 1 over R. Then it decreases, not deep gradient now compared to previous one. We saw field intensity is decreasing rapidly because it's inversely proportional to R squared. Here R, not deep curve. Then both sides should be negative potential. It's like a well. This one is a potential well, right? We all in this kind of potential well, right? Actually, inside of the earth we can plot roughly like this. Inside of the planet, inside of object, right? If it is uniform. Then basically we need normally outside potential variation. I'm going to draw here field intensity variation also. Then you can see nice relationship. Field intensity rapidly decreasing. Field intensity rapidly decreasing. I told you potential gradient is field intensity. You can see here gradient maximum, field intensity maximum. And it's positive gradient, then negative this value. And you can see here gradient decreases, then this one decreases. After that you can see gravitational field intensity decreases, potential gradient decreases at the midpoint gradient 0. Right? No need to know how to compare them, But basically you should know outside of the earth, field intensity variation, potential variation. Then here you can see at infinity, when if you want to go to infinity, you can make that potential zero, right? Because zero is the maximum value that a potential can have, right? When object is released from infinity, it comes towards earth and uh, hits the earth finally. Then you can see it comes to minimum energy level. Minimum energy level means stable. Stable. The most stable point is center of the earth for our earth because potential minimum there. At infinity very unstable because potential maximum. Right. Anyway, potential curve you should know and field intensity curve you should know. Uh, we can do few questions with this potential equation, right? You can complete this diagram also. Potential variation outside especially, not deep gradient, because potential proportionate to 1 over r, but g dash we saw 1 over r squared, therefore rapidly decreasing, potential decreasing slowly. Now I am going to do a few questions. Before doing that, I told you when object is moved away, we have to do work. Work done by us positive. When it's moved this way, work done by us negative. You have to know this principle. If work done by us is positive, if work done by us is positive, work done by the field negative. If the work done by the field is negative, work done by us is positive. It's very, very nice relationship. You can see if object is moved from here to here, here to here, we are doing work. Work done by us positive because we apply force this way to move it in the same direction displacement, we are doing work. Work done by us positive. But you know, force given by the field in the opposite direction. Then work done by the field negative because force opposite. If work done by us positive, work done by the field negative. Right? But the definition, energy to bring 1 kilogram, that is work done by us, when it's brought from into that point, that work is done by the field. Therefore, work done by the field positive, work done by us negative. That's why potential is negative. Work done by us when it is brought from infinity point considered negative. You can't remove this negative sign, never. Right? Okay. Now we can do small questions with potential. Uh, then thank you very much.